Okay, I'm gonna get started now. So what's up, guys? Welcome to week 4, lesson 7 of the guild for this semester. Today we're going to be going over recurrent neural networks, and we are going to basically start this kind of arc of text generation and understanding how deep learning models generate text. So we're going to start off from here. We're going to build towards our project where we build GPT. So really interesting week or set of weeks. Please fill out this form. This is the Airtable. We always do this, but I'm pretty sure everyone here already has it. So here's the plan. Again, like I talked about this week, today we're going to talk about RNNs. More importantly, their pitfalls, what RNNs are bad at, and how that led to the development of the transformer, which is the architecture behind things like ChatGPT, Claude, all that. Basically, the architecture that revolutionized all of AI back in 2017, and then, well, back with GPT-3 when it came out in 2022. And then next week, we are going to actually implement it from scratch. It's going to be really cool. So let's get started with sequential modeling. What is sequential modeling? It basically refers to a type of problem in which the past influences the present. This is what we would categorize text sequences as, because like in a sentence, like here, what is sequential modeling? The next word, for example, in this case, modeling, is affected by the words that come before it. So you wouldn't just put any other word here. The word that you choose for this has to do with the words behind it. Same thing here. You have like a paragraph. A very important example of this is text sequences in which the order of previous words influence the, and let's say we don't have anything here. To be able to predict what word we put here, we need to have a sense of what the previous data was. We also have time series forecasting, audio, and human behavior as sequential modeling tasks. Human behavior would be like, think of like in a recommendation system. If you searched up recently things about like working out, then the recommendation system would start recommending things like, I don't know, barbells, kettlebells, whatever. Yeah. But then that would change over time as human behavior changes over time. Then I might search up like cool things and you get recommended different things. Audio, simply because of the shape of audio, like the waves, when an audio, I don't know, it's like a wave. You want to continue the audio wave from where it last left off. So you can consider that as a sequential modeling task. And the big neural network, one of the original neural networks for this task were recurrent neural networks. We're going to talk about those now. I mean, the whole point of this is the RNNs. So what are RNNs? They are another type of neural network, kind of like CNNs and normal neural networks. There's also graph neural networks, but recurrent neural networks, the important thing about them is that they contain hidden states. These hidden states would be the past time sequences. If you see in this diagram right here, right, we have our inputs like a normal neural network, we have our outputs. But here in the recurrent, in the hidden layers, we see this kind of looping in the neural network. This is kind of how we represent the hidden states. The whole point of RNNs is we get these. Right now it's very abstract, but when we unroll them, is what we call them, you're going to see the pattern of how they work. So we unroll one of these cells, we call them recurrent cells, and you'd see, let's say in the instance of a sentence, if you want to put like what time is it? You have what, this would be the input. We pass it through our hidden state. We perform some calculation and then we have some output. This is at time equals 1. And then at t equals 2, this output would be the word that comes after. So what is, this is the input to the other hidden state. So then now in this hidden state, we have all of the content from this hidden state here, from the previous hidden state, and then we encode a new hidden state. Our output is another y t plus 1. In this case, it would be t equals 2, and so on. What is the serves as the input here? So now we have the new, what we encode inside the hidden state, and then we have the information from the past, which is this what is part. And then it's kind of like that throughout. And then this would be at y equals t plus 2. This is when we unroll all of this. This is kind of what is going on, where our input at a specific time gets encoded in a hidden state, where we maintain that information. And then that way, over time, we kind of remember the past as we generate the future. And we're going to code this up. So here's the Colab notebook for today. We are going to be using a new framework. Instead of PyTorch, we're going to be using Google JAX. And for JAX, I mean, we're going to build the intuition and build the RNNs using JAX. But then I also have, kind of like last week, some activities and some like exercises at the end to have a better understanding of JAX. So we are going to build GPT-2 in JAX. And yeah, I think it's really important to have an understanding of both tools, PyTorch and JAX. JAX is really different. You're going to see it's like fully different. So it might take some getting used to, but it should all be good still. So let me copy this over and let me share my screen. Forgot about it. All right. So here is the, I'm sorry for those online. Here is the URL for the notebook. And we're just gonna see how RNNs work. I'm gonna do like a mathematical breakdown of it as well. And then we're gonna see the pitfalls of these RNNs. So I'm gonna get started with it. Try to connect to a like a T4 or a G4 GPU before you get started. And also, this is the make a copy version. Make sure to make the copy so that you can keep like the edits that you make. But also at the end of this notebook, let me scroll all the way down. We have the final G4. P4 or G4 or whatever you have available that's not like CPU. Let me connect to mine. Okay, we should be good. And I said that at the end, we have a link to the final completed notebook. So first thing we're going to do, we're going to run these few cells. What these cells do, we know them as the imports. We're going to install JAX, pip install JAX, and we're going to import all of these tools, which we're going to use throughout. And we are going to generate this key for reproducibility. We're going to set it to 42. Let me know if it doesn't run for you. That usually is a problem with what GPU we're connected to, but we should be good with that. And we're going to talk about this. I don't know if you guys have realized when we use Torch, we kind of do torch.manual seed 42 and or we put whatever number in there. And that kind of sets a seed for the randomness throughout the like notebook. We're going to see how JAX handles this. It's really different. But for right now, let's just focus on the RNNs. So here you see a better example of a graph of how RNNs look. Let me zoom in because I always... Is this good? Yeah. Here you see kind of this backtracking layer. And RNNs are specialized for sequential modeling tasks like text predictions. They contain the hidden state. How do we calculate this hidden state? This is really important to conceptualize. The most important thing to understand is the weight matrices that we use here. Remember, the weights are the parameters that we tune as we train our models. And these, finding the optimal set of weights is basically what gives us a good train, like a well-trained model, a badly trained model, and all of that. So a hidden state. Here, I'm just going to copy down the formula and explain it. A hidden state is what goes on inside. We apply a tanh activation function, and we have a hidden weight matrix, which we multiply by the hidden state at time -1. So this basically means the hidden state at the previous step. We multiply that with a set of weights, and then we add that with a weight for the current input at time t. And then we add a bias h. So here what's basically going on, we have one, and if you see it through here, we have the input, hidden state, output. Here I'm going to put x at t -1, and this is y at t -1. This becomes x of t. We set it to here, and then there is a connection here, y at t. So what's going on here, right? We are multiplying this input value with this weight matrix. This weight matrix is the one that comes from here. We multiply that, that gives us some value. We do the same for our hidden state, right? We have a hidden weight matrix, and we multiply it by the previous hidden state, which in this case would be this. This is ht -1. This would become ht. And we add it to some bias. So here we have some number, and we apply an activation function tanh. What tanh does is it basically kind of squashes the whatever value we have here, it squashes it into a range between -1 and 1. This is to, we do this to kind of control, if you guys remember like the gradients over time, we do this to control the output so that the gradients don't get too high. And then once we multiply them over, it's gonna like explode to some really high number, which wouldn't tell us exactly what values have most signal. This is what goes on in this equation. Again, here you see just an explanation of each value, each variable within this equation. And then here you see it unrolled. Same thing, right? We have the weight matrix at x = 1. And then we have a hidden state. In this case, we don't have a hidden state because it's the input, right? So there's nothing in the past of what, in the what is time, or what time is it? There is no input for the what. We multiply those together, and then we have an output y1. And that's just an RNN cell as we know it. So we're going to test this out on a data set, decently big data set. I was going to use a really big one, but it was taking too long to train. So here we're going to load the Wikitext data set. It's just, here you see like the Hugging Face for it. It's just a bunch of like Wikipedia articles, basically. And here we download the data set. We're going to get the split for train, and let's print the data set so we can see like kind of the features of it. So this data set that we're using, the features are just text, and it has 36,718 rows of text. You can visualize that pretty well. It's just a bunch of paragraphs. When here I put millions because I was using the previous, I was using I think it's V3, which was millions, but as I told you, it takes way too long to train. And here we're just going to tokenize and batch this this data set, and we're going to talk about that now. Yep.
Oh, that.
Yeah, I mean, all I printed was this. It was just printing to see like the data set values and things like that. We just run this tokenize and batch. Don't worry about that. We're going to focus right now on tokenization. Tokenization is really important when we talk about text generation. And if you guys remember, we're going to do a little another little like introduction to tokenization. When we tokenize something, for example, when we talk about text generation, we can go either like character by character. You can think about it that way. So like hello world would be, we generate H and then we predict the next letter that goes after that, E, and then we just do this for each and every character, right? But that takes that is very computationally expensive. I mean, even if we would only have, I don't know, like 65 maximum characters we'd use, there are words in the English language like the, it, things like this that always show up. And it wouldn't be the most efficient thing in the world to have to, every time we see we'd have to predict the H and the E. Not only that, but imagine you're generating like a whole essay. If you do character by character, that's going to take a long time. And then you could think also if we do word by word. So we just do hello, and from hello, we try to predict word. But the problem with that is that the English language or language in general is too like expansive for that. We have too many like words in our alphabet. And not only that, we also come up with new words like every couple of years. So these models, these tokenizations, if we do word by word, they get outdated pretty quickly. So a way we kind of combat this is by tokenizing in specific ways. And one of the most popular encoding algorithms is byte pair encoding. And you see an example here. We basically just find like the most popular set of characters throughout a whole like data set, and we encode them as new characters. I'm going to do this same example that we have written down here. We have A, B. Just imagine these as words or whatever, right? B, I think it's 2 more A's and then back. B, A, C. So we run through this, right? And we see what words come together the most. In this case, A happens 1, 2, 3, 4 times. It's pretty sure it's the most out of this sequence. So since A comes together that many times, we're going to make a new character for it called, in this case, capital Z. So if we make Z equal to A, we have Z, A, B, D, Z, A, B, A, C. And now in this sequence, we also have Z. Well, I do ZAB actually. We can even encode ZAB as its own Y, right? So now we have Y, D, Y, A, C. And now, since we saw this combination, this AAB, a bunch of times in the data set, we just make a whole new character for it. So whenever we kind of encounter this, it's its own character and we predict it as the next token. In English, like in normal language, we would see this kind of as, I don't know, in the words predetermined and like prequel, things like that. This comes like, we see this in English a bunch of times. So we should just encode it as its own character. And we consider it its own character through tokenization. That's just an example of byte pair encoding. How are we going to do that? We can code the algorithm from scratch, and I'm considering doing it for GPT-2. Right now, we're just gonna import a tokenizer. So we are gonna import the GPT-2 tokenizer, which again utilizes this byte pair encoding algorithm. There's other algorithms also for tokenization, but we'll just use the GPT-2 one for now, since it's also the one that we're going to be using for when we make the project itself. So load it. Here's an example of a text input, and we're going to get a list of token IDs from this text input. So all we do is we encode it using this encoder. And the text IDs that we have returned are these. This, for example, how many words do we have? We have 1, 2, 3, 4, 5, 5 words, these characters. But you see there's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different token IDs. So this was in some capacity tokenized, like on, you know, E, things like that. And then the spaces, the exclamation points, things like that. And here we're making a NumPy array called X of the token IDs using, think about this as like kind of how we make our like tensors, but this is how we would do it in JAX. But right now, let's print so you can see the vocabulary size. Remember, every time we make a new character, that adds to our vocabulary size. So the vocabulary size of this tokenizer is 50,257. That means there's 50,257 different unique atomic pieces of text, kind of like this AAB, that's made into its own character. There's 50,000 of them. And now this is gonna be the difficult part. And this is where we're gonna code our RNN from scratch, but using JAX. So some concepts are gonna be kind of difficult to follow at first. We're gonna be using JAX throughout this next week or so. So it's gonna become much more intuitive to think about. But the difference between JAX and PyTorch, other than performance, let's talk about more about how we use PyTorch and JAX. It has to do with a whole philosophical undertaking of it. So PyTorch, you know that it's an object-oriented programming framework. So we create tensors, right? Those tensors are objects. When we create like a CNN, we make a class and then we initialize it with the init method and self, all that stuff, and then we do like self dot whatever, like features equals. We do all of that. We create an object in memory. The weights are stored inside this object as we update them. But in JAX is more of a functional programming framework. This results in everything being much more mathematical in a way. So we create our own weight parameters and we pass them. So let's say here we create like a matrix of weights. We have to pass them individually through each function that we make. And we're going to see this more as we work with this over time, but we don't exactly work with objects. And there are some, what's it called? Again, there's some exercises that I left at the end so we can try this out. But bear with me, it's going to be very different from PyTorch. Here, we are going to define different hyperparameters of an RNN. So we have the vocabulary size. It's an int, right? Notice how we're not putting this inside of an initialization function. We have an embed dimension, which is also an integer, and then we have a hidden size. So what are each of these? The vocabulary size is what we talked about. The 50,257, that's the amount of unique vocabulary, unique like pieces of text that there are in the tokenization, after tokenization. The embed dimension means, if you guys remember in clip, when we implemented clip, the text encoder encoded to a 568 dimensional vector for the text. So the word, like if you remember the CLS token, it would be like, 3.98, 4.10, all the way to 568 of these. That's 568 dimensions. And then the hidden size is the amount of dimensions that we want inside of our hidden space, inside of our hidden state. So we're going to use this NN.compact, and we're going to call this. Here we have X. Remember, X would be our input, and the H would be the hidden state. So X shape, when we put an input of text, we have obviously the length of the text. So the cat ran away. Whatever the length of this is, instead of tokenizing, let's just use each word. This is a length of 4. We call this the time dimension, by the way, the time embedding dimension. But you could also think of it as just the sequence length. And then we also have all the batches of this, of like sentences in the data set. So here we separate batch size and sequence length from the shape of X. This would return a tuple of batch size and sequence length. And what we're just doing is we're extracting that ourselves. And our first step is we want to, like we talked about at the beginning of a sentence, there is no hidden state because there is nothing behind it. We're at time equals 0. So we want to initialize the hidden state to 0 initially. So first we check if H is none, which means that we are at the beginning of the sentence. Then we are going to create a tensor of zeros, but we're going to create, basically think about it as numpy arrays. We're going to use JNP dot zeros. This just initializes it all to 0 of size batch size and self dot hidden size. And here we're creating basically that weight, that hidden state. And these values get updated over time. And now we're gonna do the embedding. Do it down here. The embedding is simply we have X embedded. Right, equals an embedding layer where the number of embeddings is equal to the size of the vocabulary. So that's just saying that for the sentence and for everything we have written, the size of that embedding would be the size of the whole vocabulary. And that's how we pick different embeddings for different like sentences, different words. And our features is the embedding dimension. This is what X is. So you see it, whoops, you see it right here. Yeah, so we're basically creating kind of like an embedding table. And here we want to define the cell. Remember, the cell was one of those kind of input to hidden to output states. And that's what gets repeated over and over in an RNN. So we want to define that cell. So we're going to make another, like a class for it, RNN cell, and we're going to NN.module. And this comes with its hidden size, which is an integer. And we call NN.compact again, because we're doing a call here. This is the same exact thing that we did up here, but now we're doing it just for one individual cell, right? So what goes into a cell, like what's important about a cell? We need the previous state, and then the previous hidden state, and then the current state. So we have hprev and x at time t. This here, if you guys remember the equation, this is where we compute the equation. Remember, that equation would happen at every step of the cell. And again, this gets repeated over and over, however many times, depending on the size of the sequence length. And so here we have, again, we call it, and then we're just going to compute the same equation as we did before. So our next hidden state is equal to tan h, right? So we're doing that tan h. That's our activation function. And now we want a dense layer where we have the hidden size, and we're going to call it dense x. So this dense layer, we multiply with the x at time t. And then we also do the same thing for the hidden layer. So dense self dot hidden size. Size of hidden, we name it dense h. So as you can see, we're basically making our own parameters, right? We don't have, we're making like our own equation here and passing our own parameters through. And it's going to be, again, very trippy once we start actually training this. So here, we're going to return this. We're going to return a tuple of them. Give me 1 second. Okay. So we're going to return these two. So that we can treat one of them as the output and one of them as the hidden. In this case, it would be the same thing. And now we're going to use this specific function called rnn.scan to do a sequence-wide loop. So instead of using a Python for loop, which would have to go between the CPU and the GPU, in JAX, what we do is we scan the cell through a sequence-wide loop. So for every sequence, JAX does its own loop and kind of just sends it all to the GPU. This is how we would go about that. So we create the scan cell, and here we put in the RNN cell. So that is what we're going to be computing all the time. Variable broadcast is, we're going to set that to params. This basically means that the parameters that we're going to pass, I don't know if you guys have noticed, but throughout all of these loops, we are reusing the same hidden weights and the same input weight. It just happens each and every time we loop over it. So this means that we're going to broadcast those parameters throughout the whole loop. And we are not going to split the, this is another weird thing about JAX. It doesn't set a global random variable. We have to kind of declare it for each function that we do. And in axes equals 0, out axes equals 0. This means that we are going to, we're going to do this loop along the 0th index. But remember what we talked about, and we're going to do this now. We're going to swap this the axes. But what we're doing here is for an input of size batch, sequence length, and the time, the embedding dimension, we are going to loop through this first index, through the 0th index, my bad. Now, we want to do this for the sequence, so we want to loop through the sequence. So at one point, we're going to have to swap the axes so that our dimensionality looks like this. And that's our next step. So first, we're going to do this same loop, but for a hidden size of self.hidden size. And again, we're going to swap the axes for the scan. In JAX, this is really simple. We call this time, what was it called? It was called, we call this time major, I think. Hold on. I'm sorry. One second. Just want to get the specific name for it. There's a specific name that we call it when we just put like the time first. Let's just call it literally time first. And what we just do is we swap the axes using JNP dot swap axes. And what we do is we want to do this for X embedded, but we want to flip the 0th index with the first index. So this gives us this resulting dimensionality. And when we get the H final, so the final hidden state, this is what we return here, right? We get the final hidden state and we get the outputs. This will be equal to this scan cell. Again, we're not using a for loop, we're using a specific function in JAX that allows us to do a for loop, basically, a loop exclusively in our GPUs. And we're going to pass H and X time first. So let's look at our scan cell. We're just saying that for a hidden state, we want to apply that multiplication in a hidden state for our H, and then for X, but X, we want to make sure that the time dimension is first. And we just want to, after we get some outputs, we just want to swap it back and project it to the vocabulary. So outputs, again, we want to swap them again, 0 and 1. So now this literally takes us back to batch, sequence, and embedding dimension. Bless you. And now we want to calculate our logits. Remember, our logits are like our final, our raw output number. So we do this with a dense layer of self.vocabulary size. We're going to call it, let's not call it anything for now. And we just pass the output. So the output dimension, we are projecting it into the vocabulary size. And we just return logits and final, the final hidden state. The reason we keep the final hidden state, we're not going to do it here, but sometimes we want to do like sentiment analysis and things of that nature to know like if the sentence is positive, if it's negative sentence, like, I don't know, like in movie reviews, the final hidden state kind of, instead of just generating the next text, it gives you kind of like a summarization of the text before it. And run these cells. Here we create the train state. So here we basically create these variables ourselves. And now let's work on the loss. We're going to use, again, text generation is kind of like a class. It's a classification because we are predicting to what class. The class would be the vocabulary. Some value in the vocab size, what class best fits the sentence that we have previously. So the way we compute the loss is through a cross entropy loss, since it's a classification task. And here, the way we do this, we get the batch. So our batch contains an X and a Y. By the way, when we have an X input, let's say it'd be the sentence. The Y for this the would be sentence. It'd basically be shifted 1 over, right? The sentence is cool. Here it'd be is, here it'd be cool. Sentence is cool. So we have, for each X input, our output would basically be an offset of that sequence. And we want to compute, we basically want to run this whole function thing because we want to get the logits and the final hidden state. So we get the logits and H. And the way you do this, we apply function. And the parameters are, well, params. Those parameters would be all the weight matrices that we have. In this case, it'd be the hidden weight and then the X input weights. And we want to pass the X and the hidden state. What's going on here is we're basically, for each input that we have in the batch, we are going to run the whole RNN cell where we have the input, we have an output, we keep a hidden state. We do this throughout this And that's basically what we declared up here. And we are applying that same function to get a set of logits. And from here, we compute the loss. So the loss is optax, which is a library within JAX. Soft, this one's going to be a long function, softmax cross entropy loss, or cross entropy with integer labels. And we pass in the logits, we pass in the true y, and then we want to get the average of it. And we just return the loss, and we keep the h as well. And let's just define our train step. Don't worry about that too much. We're going to see how this works, and then we're going to see how it fails as well. Okay. So let's go to training. Here we're going to declare the vocab size. The vocab size is the number, basically the vocabulary size of our encoded text of our tokenizer. Our embedding dimension, we'll put 128, our hidden size 256. We'll do it for a batch size of 32 and our sequence length of 35. That means a sentence would be 35 tokens long. We're going to set a learning rate of 0.003, 0.001, sorry. And we're going to do this for 5 epochs. So first we're going to get like the batches. Just this here. And we are going to get a list of like the X's and the Y's from our batch, from our different batches. And we're going to stack them together. This might take a little bit. Well, it didn't take a little bit at all. So here we're going to define our train epoch function. And let's think about this through. So we're going to define a carry. When we talk about carry, what I mean by carry is that every step here, we keep the parameters from this step and we kind of carry it over to the next step for all the upgraded things. So then that would be like the HH, the input weight as well. All of that gets carried over to the next step, and so on. That's what we call the carry. So each carry has three different things. We have the current state. So the state would be all those parameters. We have the current hidden state, H, and then we also have our current RNG. Remember, we're keeping our randomly generated number. We keep it with us throughout all of everything we work with in JAX. And then our X and Y's are the data, like the data of that batch, which we define here. So now we got these three variables that we could work with. And then one thing, like I said, we don't have a global randomly generated number for our reproducibility. So we have to define a new one every time we want to have a new function. So first we're gonna do this call it just sub key, where we split our current key into two. So our current RNG, we split it, and we're going to use this sub key for other formulas. And now we're going to define our grad function. Our grad function just means the function we're going to use to calculate the gradients. This grad function, what we're going to do is use this thing called values in grad. What this does is it computes the loss and then it calculates the gradients automatically for you. But we're going to do this based off of the loss that we made. So if you remember, we defined the compute loss function at the top. And we're just going to put has equals true. But what this is just doing is that it's using this loss. It's using this loss to calculate gradients and then to calculate the loss and then update the gradients all automatically. So it is an auto diff engine, like we said before. And then that's setting the grad function, right? And now we're going to get the results. So first we want the loss, we want the next hidden state, and then the gradients themselves. and we get them from this grad function, where the parameters that we want to update are the current state.params. Remember, the params are the WHH and the WXH. Remember, like the parameters in neural networks, whenever we train, what we want to change is always those weights. We always want to optimize them. And then we're going to apply fn. This is the function that we do to move from one step to another step. Passing on top of x and y, our current hidden state, and then we want the subkey so that our numbers kind of so we can reproduce this. And then how do we get a new state? We calculate our new state with current state dot apply gradients, and we set the grads equal to grads. And here again, you're seeing that instead of a for loop, we are using this thing called jax.lax.scan. This again scans through all of the batches and calculates the gradients for them all in like the GPU without you having to, because the problem with you doing a for loop is that it would bounce back and forth between the CPU and the GPU. This makes it a lot faster, especially when we train with things of like a TPU, specifically for Google, and like this T4 family of GPUs. It helps make it a lot faster. So here, the only for loop we're going to be using is for each epoch, but we're not going to do it for each batch because the batches are taken care of in this train epoch set. So what we get here out of this, we get the state, the average loss of the current step, and the hidden state along with the random like number we generated. When we do this with the train epoch, we put the state, x all, y all, h and RNG. The h, sorry, and RNG. X all and y all, we defined them here. So remember when we stacked all the batches together? Where were we? We were here. And now we're going to run this loop. It should, if we're connected to a GPU, I don't think it would take too long to train. I hope we can train it. So then once we train it, we're going to see, whoa, I put values in grad. That's my mistake. It should just be value and grad, if I'm not mistaken. That was the error there. So it's value and grad, not values in grad.
Where's the error?
So the error is in this line where we make the function. It's value in grad. I put values with an S, plural. Yeah, you always got to watch out for those little things. It's always some spelling mistake that.
Well, mine says RNN cells not defined.
Did you run the code up here? It should be this one. Did you run?
Yes, I did. Oh wait, I put the extra. Is it just RN cell or just RNN cell?
It's RNN cell.
Oh, I misspelled it. That's why.
What'd you put?
I put like only one in.
Oh, that's okay.
Okay.
It should work from there.
I'll just have to.
And then this trains. Let's see how long it would take to train. I'm just training on 5 epochs because I'd love to give an example. But then the most important thing here is to talk about the vanishing gradient problem, which we used to use RNNs a lot for all of these text-based tasks. But the problem with them is that they had this thing called the vanishing gradient problem. We'll talk about this now while this trains. Let's see, it'd take us 6 minutes to train, so might as well get to that. I wanted to show you guys what would happen, but I think it'd just be better if we go straight to that. So fatal flaw, while that trains, let's talk about the vanishing gradient problem. If you realize we are using the same set of weights throughout each and every step. We're not doing a whole new set of weights like in deeper networks like CNNs. I don't know if you've realized, but the hidden state or the hidden layer of an RNN usually isn't that deep. Compared to a CNN, CNN is like layers here and then layers here and then like 50 of these. Remember the ResNet 50 was 50 layers deep. This normally is just our input, maybe a couple hidden layers where we do our RNN cell, where we unravel this, and then our output cell. This means we are using a very limited amount of weights. So then why is this a problem? When we calculate the gradients of these weights, realize that through time, this is called backpropagation through time, we are going behind each time step and we're multiplying the gradient of the weight basically by itself over and over. So think about what happens when you multiply. I put an example here, but if you multiply 0.9 times 0.9 times 0.9, and you do that for a while, you start approximating zero. So your gradient effectively vanishes, as we say. And when we lose the gradient, we can't exactly compute the new weights of the model. Do you guys remember the backpropagation lecture last week? It's really important that the flow of the gradient maintains like some level of information. But when we lose all of that information, this causes RNNs to forget a lot, be very forgetful in a way, since we can't update the beginning of the model throughout the time steps. So I put an example here of a failure that we had last year. This is text generated by an RNN. You see, it says, once upon a time, earn a father who can also senior year, the British withdrawal of the SSI, right? It completely loses any sense of like logic within the sentence. This sentence, yes, it's English, but it doesn't really make sense because remember, as we have more and more time, so that would be like more and more inputs. Imagine each of these as a hidden state, or actually you see it right here in this picture. See how little the first hidden state has on this new hidden state, the effect, how small it looks. By the time our gradient reaches our initial layers, it's already like close to zero. So it's already like, it barely can fix the weights at that point. So for example, in a sentence like, I am in France, I don't know, cool place. Cool place, and then we just say, I went to a restaurant. The waiter spoke to me in blank. By the time we know that what is the waiter probably going to speak to you in French, but since the gradient has it's lost all the way till we get back here, right? Effectively, the model doesn't even remember that you're in France. So it's just going to put something, it could be French, but it's not going to do it because it knows that you're in France. It's just going to put in some random, Spanish, something that makes sense theoretically, but given the context of our sentence, you can see that the model forgot. And so what is the solution? What was a solution, an initial solution to that? An initial solution to that problem was a GRU and an LSTM. So an LSTM stands for long short-term memory, and we're going to focus on that one primarily. This is an example of an LSTM module, of an LSTM cell, kind of like the RNN one. here we introduce 3 different things. And first, let's see how the training has gone. Training. Okay, we're on our last epoch, and we're gonna see what type of mumbo jumbo text this RNN generates.
Yeah, I tried. I'm gonna get a little behind, kind of behind, because I was looking for error and spell it.
It's okay, don't worry. Just follow through here, and
Yeah.
we'll see. So, like what we talked about. All right, we saved it. So we're gonna start off with once upon a time, right? And we are going to basically generate these are the tokens of the seed of this once upon a time. We're going to generate 11 new tokens. So we're going to try to generate a new sentence from once upon a time. We're going to see, I think by this point, we only trained on 5 epochs, right? So you see that the loss is pretty high. But our focus is mostly going to see, let's see if it speaks English back to us. And we're also going to see some kind of vanishing gradient issue, again, where it forgets the context of the beginning. I hope. Let's see this. Okay. Nice. So this RNN model, we trained it on 5 epochs. It's telling us, it's making this really awesome story about once upon a time, Eucharist, who also means more directly to the government. Also, almost these fortifications of these indications that the governance of 3 to 30. You see what I mean? Like, yes, it spits out English words, and it seems to be very like politically motivated, right? It's talking about Congress, it's talking about government. So it has some sense of English, right? But this makes no sense, right? The sentences make no sense. There is a point where you just lose logic of the story from the first line all the way to, the third lines. And then obviously we have some non-English words. That's because we barely trained this. But what happened, right? Here's, again, what we talked about, the decay of information through time. The gradients become extremely small. And I mean, we use that example as 0.9. If you already have a gradient of 0.2, and then you multiply by itself 0.2, and then you do this like 4 times, you're gonna start approximating 0. And again, that means that the model is the signal is very low, which is not telling us enough information that, over time. And that's one of the bigger problems that we had with RNNs. And that's why we had a temporary solution of an LSTM. And again, here's the LSTM block. See if we do the math here. The LSTM, what it introduced was 4 different gates. We had a forget gate, an input gate, an output gate, and then we had this cell. And just to summarize what it does, you see this addition here in a way so that we don't have to multiply, throughout each step. We introduce some level of addition so that it at least separates itself from 0, the gradients over time. So it has a little bit of a longer memory. And you see here, we input our time and our previous hidden state. We pass it through this sigmoid, and then we multiply it with the cell state. This FT is our forget gate. What the sigmoid function does, I want you to just think about this in general for the forget input and output gates. The sigmoid function, which is what we're using instead of tanh, remember tanh squashes to -1 and 1, but sigmoid squashes to 0 and 1. So the forget gate is just, we want information that isn't important anymore. We forget that. The input gate, we want the most important information to stick with us, and same thing with the output gate. I just want you to think about in general, like when we pass this addition right here, this multiplication, we pass it through a sigmoid. Basically, the closer it is to 0, anything you multiply by 0 is just 0, right? So the closer it is to 0, it's our way of saying like for example, for the forget gate, like, okay, I want you to forget the things that are closer to 0, and I want you to remember the things that are closer to 1. We do the same thing with an input gate and an output gate. We run these concurrently multiple times. So as you can imagine, or as you can see here, we have now a weight. We have like a weight, a final weight. We have an input weight. We have an output weight along with the hidden weights and then the other input weights. So yeah, we introduce more weights and more parameters, but now our memory is much longer because we perform these operations in a way to keep relevant information important throughout the thing. We don't forget that much. Now, the problem with LSTMs, and I don't think I have like you can just run this through. There's no like code along portion here and see. I don't know what, there were some optimizations I had to do to the training, but let's just stick to the theory of the LSTM for sure. The LSTM effectively like helped with a lot of the vanishing gradient issue, but it introduced a new problem. Again, we talked about how it has 4 new weights basically, and then it like on top of that, remember you can't generate, not explain, you can't read in an RNN. You do it sequentially, right? So you go with this one, then you go to the next one, then you jump to the next one, and this would be like, what is the, and then all the way through. This sequential and linear generation takes a lot of time, and it's not like optimized for a GPU. A GPU, you could probably do a bunch of these at once, but this LSTM, the way that we generate things is not, it doesn't read everything at once. It reads everything, one by one. And that kind of introduces us to the transformer, which is the architecture behind ChatGPT. We got this issue. So we started off with the RNN. The RNN had the issue that it forgot things. It doesn't remember the beginning of sentences. So vanishing gradient. We had that. We built an LSTM. LSTM has a new issue. Let's just say it's inefficient. It does everything, one by one. So that's when we introduced a transformer.
Sorry, I have class for later. Is it okay for like work stuff?
Yeah, no problem.
It's all good.
And that's when we introduced the transformers. This is the model. This was back in 2017. This is the model that effectively was the backbone of the architecture behind GPT models. And from there, we started this like AI boom that we have right now. This all started again through text generation. Here's kind of the flow over time. Another thing I didn't talk about is GRUs. I'd say if you want to study those yourself, it eliminated one of the weights that LSTMs used, but still, we still have that kind of sequential problem that we couldn't optimize with GPUs. And we're going to see how transformers utilize this thing called attention to make text generation and remembering things over time much more efficient. And I mean, we can kind of finish off there. I have back here, all the way down here, we have a little Google JAX tutorial. Let me talk about that real quick. So JAX is a functional programming based auto defension, and it uses NumPy syntax, but combines it with XLA and vectorization. So it's basically this really big, powerful compiler, which makes it really effective for GPU and CPU training. Let's just do like a couple examples just so we can get more used to the syntax. So here we import JAX, and we import jax.numpy as JNP, and we import numpy as NP. And I just want to say that JAX arrays look and feel exactly like NumPy arrays. So if you've ever used NumPy, you know that you create the arrays like this. In JAX, you literally do the same thing, just J and P in front of it. Think of these in a way as our tensors, as we would in PyTorch. If we print both NumPy, X and P, if we print both, we get, same results, and you could even do math on it. Here we do a dot product. If you remember a dot product, 1 times 1, 1 plus 4 plus 9, that's 14. And the difference, another big thing is different from NumPy or PyTorch, it's that it's immutable. So once they're created, you can't really change them in place. So for example, you have this NumPy array, and the 0th index, you want to change it to 10. You just do kind of like a normal array. At index 0, you set it to 10. In JAX, let's see what happens if we do that. So again, let's define 1, 2, 3, and then all right, OG JAX, okay, yeah, I guess. And let's do X GMP of 0. Let's set it to 10. What happens here? We have an error, right? Because JAX arrays are immutable. You can't change the JAX array once it's already declared. But instead of doing that, we use this. We make a new, okay, I think this code cell already deals with that. We use this new syntax in which we create a new variable, and then we just say at point 0, at index 0, we set it equal to 10. And this way, right, is how we do that switch. And then the big thing, another big thing that's really annoying to deal with is randomness. And I say it's annoying to deal with because if you have like a PyTorch background, it's like really different to what you're used to. But here, for example, we did this at the beginning, but let's do it again. We're gonna create a random key of, let's always just do 42. You can put this to whatever. It just sets the randomness, the key. And then here we see the key is the same throughout, right? So if I want to make a new variable with different numbers, it's not going to automatically do it for me. I have to declare it myself. So we have to split the key every time we need a new random numbers. Because what happens, again, let's do another print statement where we do another random variable. We do random.normal. And we do this size 3. It just prints literally the same numbers. So we need to split the key so that we can have different numbers. And then if we want more different numbers, we split the key once more. Right? So these are kind of a few of the things that we have to get used to. But alongside that, we get these like superpowers from JAX that, I should have added pmap, but we basically have jax.grad, which automatically computes the derivative of our function, but we've worked with it ourselves instead of letting PyTorch like automatically randomly do it. Here we declare it ourselves, so we get to actually intuitively see the math. We also have jax.jit. This is just-in-time compiling. This allows like training to be really fast. We have vmap, which vectorizes the function. We use this at the top, where if you remember, we didn't use the for loop. We scanned through the whole batch. And we also have pmap, which stands for parallel mapping. Same thing as this, but parallel. And let's just see the way this works. Let's make a function f of x, and we want x to the 3rd power plus 2 times x, right? And we want to compute the gradients. We do df dx equals jax.grad at f. And then if we want at 0.2, we'd get our 14. For JIT compilation, it, obviously this is a very simple function. It's not going to matter here, but when it comes to more advanced, bigger neural networks, this comes in handy a lot. And then same thing, VMAP. We could have a batch of X's. For example, we make them a NumPy array. And we want to batch them. We just do jax.vmap f, and then let me print that. Let me just print it on this line. We will get 3, 12, and 33. We're batching these, I believe. Yeah, because we're passing function f, like this function right here. We are just mapping this to that function and allowing it to compute all of that. So those are just a couple of things. I'd say for this week, we're going to focus on JAX a lot, next week as well. So I'd say look up maybe like a short tutorial on YouTube. Go back to this notebook here at the end. We have a couple of the functions, and just try to get more used to the syntax. I know it's very different. And again, philosophically, the way you think about JAX is very different from PyTorch. We're used to object-oriented programming. But again, here we pass functions in and everything's like a mathematical function. But other than that, we are done with today's lesson. On Wednesday is our Transformers lecture. Again, we unlock the architecture behind ChatGPT. It's this beautiful architecture. The most important thing here is the use of attention. And yeah, so we'll meet in OI EHAN 105, and yeah, pretty much that will be our Transformers lecture. And then on Monday, we're going to implement it from scratch. So thank you all that came. Thank you all of you online, and I'll see you guys on Wednesday.